Okay, I'm going to talk about section 8.8, power series. Power series are infinite series that have a variable, typically x, in the expression. If you think about what we were doing in the section before this, 8.7, we were talking about Taylor polynomials. Taylor polynomials would have a finite number of terms. One way of getting a power series, one way would be to take, for instance, what we did with those Taylor polynomials and then extrapolate that out to infinity. So when we talk about power series, we are talking about an infinite series. There's two different ways to express power series. You should be familiar with both. You'll be asked to do both at different times. The first is just using sigma notation, starting at some value. Doesn't have to be 0. In fact, any of these we could write using whatever index that we choose. So for instance, this one, you can get the exact same thing. And this is something that's important to realize because at different times it's going to be important. I could set that at, n equals 1, and this would be n minus 1 x to the n minus 1, and that gives us the exact same thing. So the beginning index really doesn't matter. So the two different ways to write these things out are going to be in sigma notation and then in this expanded form. The expanded form that they accept on the AP test is they want the first 4 non-zero terms and then a general term. Notice I put the ellipses here and then also here indicating it continues on. When we did the Taylor polynomials, you notice when I did the notes, I did not have that continue on. We want to show that this is going to infinity. So typically you'll be asked to do it as sigma notation or an expanded form, usually not both, but it could be. So another thing we want to talk about power series is where they're centered. The center of a power series might be generated the same way as we do the center of a Taylor Taylor polynomial. And we'll do more of this connecting in the next two sections, 8.9 and 8.10. So a power series centered at 0 looks like this. Notice there's no term here. And then a power series centered at x equals c. We're just replacing the x with x minus c. And that's about it for power series as far as the form. Now, a big part of this chapter, or this section, will be determining what is called the interval of convergence. So what we're going to find is these power series will typically equal a particular function for a particular interval of convergence, and that's what we'll get into now, is finding some intervals of convergence. Okay. All right. Okay, example 1, we're going to start really basic here. So we want to find the center, the interval of convergence, and what is called the radius of convergence. This is actually one we did earlier, and really this is quite nice because we can see this is geometric. Now before I do that, realize the center is just based on this, so my center in this case is just simply 0. And now what I want to realize is I can really see this as a geometric series, right? So a geometric series would be a to the Rn. The fact that this starts at 1, that doesn't matter here because we're not looking for necessarily what the function's equal to. If we were interested in what the sum of this thing would be, we'd factor out the x. But anytime we can see this as geometric, and geometric means basically you can write it so it's 1n and there's no n outside, we can basically do the interval of convergence really easy. So since the series is geometric, so just like this, except r is not a constant, it's x. So since the series is geometric, it's actually quite easy because I know that this thing will converge, our interval of convergence here. So interval of convergence is what x values make this thing converge. It will converge when the absolute value of r, which in this case is just simply absolute value of x, is less than 1. And it's that easy. So right away, -1 is less than x, which is less than 1. And this is our interval of convergence. So this is what we refer to as the interval of convergence. So if it's geometric, it's that simple. And we saw these earlier in the chapter. Notice the 3 we could consider as part of the A. In fact, the A, we would factor out the x, so it'd be 3x, but that doesn't really matter here. That doesn't come into play as far as the interval of convergence. Okay, and then the radius of convergence, understand what this means is, and this will become important later, why we talk about an interval versus a radius. So here's our interval. It has a center at x equals 0. If we think of the center as being the center of the circle, and -1 and 1 being the endpoints, this would be the diameter here. Radius would just be half that. So basically from your center to your endpoint is your radius. So our radius of convergence here is equal to 1. And once you set this thing up, you can always tell right here what you're going to end up getting, and I'll talk more about this. Once you solve, if you get x minus c, it's less than r. This is the radius of convergence. Okay. If that works, great. If not, you can always just look at the center to the endpoint. Okay. So if it's geometric, really basic. We've been doing those way back when. Now let's look at a situation where it's not geometric. It's going to be a little bit harder to find the interval of convergence. Okay. Example 2 is a little more complicated. And so we're going to do all the same stuff, find the center and the interval of convergence and the radius of convergence. The center, you can tell right away, the center here is going to be -3, okay? So x minus c, so c is going to be -3. So that's our center. We know that right off the bat. That's pretty easy. The next thing we want to do is rewrite this in a way so generally what we're going to look to do, if we can write it so, you know, it doesn't matter what stuff is outside, as long as you can write all of your x minus c to 1, and this could have constants in it, it really doesn't matter. If there's anything outside an n, then I can't just use geometric series, and we'll talk about that. So just let me point out that I can rewrite this thing with the 5 and this term raised to the n. So this will be x plus 3 over 5, that's all to the n. And then we have 1 over n squared outside. So since I can't get, you know, so basically if I can write where there's 1 n, I can do its geometric. It's going to make life a lot easier, trust me. Since we have that 1 over n squared or the n squared in the denominator, I cannot use geometric series test. So we saw this a little bit, but very, very briefly. What we do is actually, if we can't see it as geometric, we go right to the actual ratio test. So what we're going to do here is we're going to let a sub n equal x plus 3 over 5 to the nth, and then 1 over n squared. And then we're going to do the limit as n goes to infinity. So we're using ratio test here. So a to the n plus 1 over a to the n. Always do your labeling first. That way, if I start canceling and doing all sorts of crazy stuff over here, I have that. That's going to cover that part of the rubric there. So this is going to be the absolute value of x plus 3 to the n plus 1 over 5 to the n plus 1. We'll put this in the denominator. N plus 1 squared times, and then the reciprocal. So this will be 5 to the n squared over absolute value of x plus 3 to the nth. You'll notice the only thing I'm putting in the absolute value is the thing that could possibly be negative. All these other terms are going to end up being positive. So what's going to happen for large numbers is, you know, this will become 1. This will cancel with this, just leaving with 5, and, you know, of course we can write that as 5 to the n times 5. And so this whole thing cancels. This will cancel with this, and we're left with the absolute value of x plus 3. Okay, so now what I get is the limit as n goes to infinity of the absolute value of x plus 3 over 5. That's less than 1. Okay, so I'm going to put that on the other side. I get the absolute value of x plus 3 has to be less than 5. Okay, so here's the deal. Right away I know my radius of convergence. My radius of convergence is, once this is solved, whatever's over there, that's my radius of convergence. So we have our center. So those two things are pretty easy. Here's the deal. As we talked about before, geometric is really nice because there's no ambiguity. If this is equal to 1 with the geometric series, that's it. It diverges. With the ratio test, keep in mind, if this is equal to 1, then it's inconclusive. So here's the deal. Our interval, so we're going to have, anyway, let's solve this. -5 is less than x plus 3, which is less than 5. So subtract the 3, that's -8 is less than x, which is less than 2. Here's the deal. At -8, this thing's equal 1. At 2, this thing's equal 1. So at both of these points, I don't know whether this converges or diverges. So I have to come up with another test. And I'll tell you basically the other test typically is either going to be a p-series thing or a combination of p-series and then perhaps the alternating series test. If we have a scenario where it's going to diverge by p-series, you have to check whether or not you're going to have an alternator, which means we use alternating series test. So what we have to do is we have to test both these points. Now, hopefully I'm not throwing too much at you here. We have to test both of these points. I want to point out that I have 1 over n squared, and that's why I wrote it this way. If I plug -8 into this, for instance, I'm going to end up with an alternator, because that's going to give me -5 over 5, which would be -1 to the nth. Okay? So that's -8. If I plug 2 into that, I don't have an alternator. But it doesn't matter, because this thing's going to converge whether there's an alternator or not by p-series. So I can actually test both these points at once. And I'll show you what it looks like if we need the alternator in our next example. So what that means, like I said, if I plug in -8, this will be -1 to the nth, 1 over n squared. If I plug in the 2, it's going to be 1, so I'll just call this plus or minus. Now, I don't really care about that, because if I take the absolute value of this, I can just do absolute convergence. Right? I don't need that alternator for either one of these, because p equals 2, that's greater than 1, so this thing converges by p-series. So now I have everything I need. So here's my center, c equals -3, here's my r. This thing converges both for -8 and 2, so my interval convergence is -8 is less than or equal to x, which is less than or equal to 2. Okay, let's do an example where we have to do the endpoints independently of one another. We'll do the exact same thing. Okay, so example 3, we're doing the same thing. The center is equal to 0 if they ask that. And then from here, realize that for the interval and the radius of convergence, I can't write this as geometric. The only way I can write this geometric if I can put everything to a single n. I have that n outside of that, so I have to do the ratio test. That's the only option. So a sub n is equal to our term here. Just get in the habit of doing that every time. The limit as n goes to infinity. A sub n plus 1 over a sub n is equal to the limit as n goes to infinity. So this will be the absolute value of x to the n plus 2 over 4n plus 1 times, and the reciprocal for the n over absolute value of x to the n plus 1. Once again, notice that I really only need absolute value around the things that could possibly be negative. These things are always going to be positive. Okay, now let's just think for large numbers. Realize if I distribute this for the n plus 4, the plus 4 is negligible, so for large numbers this will cancel, giving us 1. Here what we're going to get is, let's see, x plus 2. No, so this is just going to be 1 and absolute value of x. Yeah. So what we're going to get here is absolute value of x. This is less than 1. So right away I can tell what my radius is. The good news is if all they ask is the radius, which does happen sometimes, then I don't have to do anything with the endpoints. So the first thing is, if we're doing an interval convergence, it really is about, the endpoints tend to be the thing that sort of stresses us out a little bit. So if we can see it as geometric, we don't have to test endpoints, number one. Or number two, if we have a radius that is, or kind of space there. Or if it's geometric, or if they just ask us for radius, excuse me. Okay, so anyways, if I solve this, -1 is less than x, which is less than 1, I don't know what's happening at the endpoints. Now this one, because it's a single n, basically what's going to happen if I plug -1 into that, I'm going to have an alternator, and this thing will converge. If I plug 1 into this, it's going to diverge because of p series there. So I have to go ahead and do this individually. So, and they're not asking for whether it converges absolutely or anything, so I don't have to do that proof. So first of all, I'm going to test the x equals -1. So that means I have -1 to the n plus 1 over 4 to the n. By the way, the 4 in the denominator, I don't really have to worry about it. I could always bring that out front as just simply 1/4, or I can leave it in there like this. So what I realize is, number one, 1 over 4 to the n is greater than 0 for n greater than or equal to 1. 2, the limit as n goes to infinity of 1 over 4 to the n is equal to 0. And 3, 1 over 4 n plus 1 is going to be less than 1 over 4 to the n. Okay, so we would say now that this thing converges by alternating series test. So we know this thing converges to x equals -1. Now let's see what happens at x equals 1. So at x equals 1, we're going to test this. And what I'm going to get is sigma n equals 1, the bottom limit, to infinity. If I plug 1 into this, I get 1 to the n plus 1. Realize that that just is 1, right? So this is just simply equal to, let's rewrite this in a way that I'll just apply p-series, 1/4 sigma infinity n equals 1. That's just 1 over n. So this thing's going to diverge. So p equals 1 diverges by p-series. So now my interval of convergence, -1 is less than x, less than or equal to x, which is less than 1. So it converges at x equals -1 because that gives us an alternator, but diverges at x equals 1 because it diverges by p-series. Okay, so that's interval of convergence. So that, once again, to sum up, if we can see it as geometric, for instance, if we can write everything so it's raised to a single n, not an n outside like we have here, then you can do geometric. You just find what the absolute value of r is, find that interval. We don't have to test the endpoints because with geometric series, they always diverge at 1 and -1. If it's not geometric, then I have to do the ratio test, and then what I'm going to do is I am going to determine whether it converges or diverges at each endpoint. Some things that you're going to see happen, and I'm not going to do examples like this, but we'll definitely see this in the book. Sometimes our radius of convergence ends up being infinity. In those cases, I don't have to test the endpoints because it's going to converge for all real numbers. And also another thing is we could get a radius of convergence at 0. So it turns out that it actually diverges for all values except at the center. These things always converge at the center. Just like Taylor polynomials are always accurate at that center, or 100% accurate, these things will always converge at the center, even if the radius of convergence is 0. Okay, the last thing I want to talk about today is finding derivatives and intervals of power series and how we're going to do that. Okay, so now what I'm going to show you is how we integrate and derive these things. So let me just point out that we're calling f of x equal this power series. This is something we could certainly find the interval of convergence. It's not geometric, but it wouldn't be too bad. And that's something you might do at some point where they have you do a combination of derivatives and intervals. But there's nothing different here. We would just do that like I showed you before. So now what's going to happen if we derive? I think to start off, and what I'll tell you is that to start off, to just see what's happening, let's do this in expanded form. And then once we see what's happening in the expanded form, Let's see if we could just leave it like this. There's kind of a little adjustment we have to do. So let's write this out in an expanded form. So this will be x plus 1/2 x squared plus 1/3 x to the third plus 1/4 x to the fourth. And once again, when we do these expanded forms, it's pretty much the standard on the AP test. They have you write 4 terms and then a general term. So this would look like this. Okay, so we're going to take the derivative just like we always would. These are basically polynomials, just infinite. So this would be 1 plus the 2 comes down. That gives us 1x. The 3 comes down. That gives us 1x squared. Plus 4 comes down. That goes to x to the third. And then down to this, the n comes down, and that gives us x to the n. Okay, so what does that mean for this? Well, let's take a look at what we could do here. Basically, you'll see when we take the derivative, so this is equal to f prime of x. When we take the derivative of these things, you just basically treat x's like x's. N's, or any numbers, n's are constants. What we have to keep in mind is n's aren't variables because they're always, in each term, end up being a number. We don't know necessarily on the front end what it's going to be. Well, we do. It's going to go through all the numbers. But for instance, n is 2 here. N is, n is 1 here. N is 2 there. N is 3 there, et cetera, et cetera, et cetera. So what happens here is this is going to come down and we get n x to the n minus 1 over n, right? So just take the derivative, n being a constant, and what we end up getting is the n's to cancel, and you'll see we get the same thing. Now, I want to point out, and sometimes you have to be careful with the index, does n equals 1 work for this? And the answer is yes. If I plug 1 into this, that's going to work, and I'm going to get 0. So now my new series was n equals 1, x to the n minus 1. So if I was just asked for the derivative of this, so this is f prime of x, I could just deal with this in that form. Notice nothing changed here. All right, if I plug 1, I get that second term. It's good to check. Now, what happens if I take the double derivative? And this is the one that we're going to have to be a little careful of. So if I take the double derivative here, let's first look at the constant form. Sorry, this is kind of cramped here. So basically, this goes right here, okay? So if I take the double derivative of this, this gives us 0 plus 1 plus 2x plus 3x squared plus, now let's go ahead and do 4 non-zero terms, even though, so our next one would be, the next one would have been x to the fourth, so that would be 4x to the third. So this will be n, x to the n minus 1 plus 1. Now, if we would have dealt with it just like this, so let's go ahead and look at this series. The n comes down, that's n minus 1, and then it goes to x to the n minus 2. If you kept the index as n equals 1, look at the problem I would have. If I plug 1 and I get the 0 here, but here I get a negative exponent, and that's not what's happening here. So what I have to realize is, this term, this was our n equals 1 term. Once we get a 0 term, basically that term goes away, so now we have to reset this to n equals 2. Okay, so now n equals 2 gives us what we want. So if I plug in n equals 2, I get 1 and then x to the 0 power. So that gives us what we want. N equals 3 would give us, 3 goes in, that's 2, and that's x. Now if you're sitting here thinking, I would much rather not deal with that, then you can expand these out every time. I think if you look at the textbook videos, they do that. I will just tell you, in some cases, it's going to become quite cumbersome to expand these out to see the pattern each time. So let me just regroup. If you're taking derivatives, basically it's this simple. Before you take the derivative, check that first term. If that first term is a constant, then we have to raise that index up by 1. If your first term is a variable quantity, then it's going to stay the same. And basically, if you think about what derivatives do, the variable quantities, it doesn't zero out. It's going to stay there. It's going to end up being some constant. So that term isn't going to go away. However, if your first term, so here our first term is going to be a constant, okay, then when I take the derivative, I can leave everything as is. I can bring that n minus 1 down, that drops to n minus 2. I just have to remember to raise that index by 1. So if the first term, so if we're just leaving it like this, and I'll show you what I mean here in a second. If our first term is a constant, then we have to raise the index up by 1. If your first term is a variable quantity, then you can leave the index the same. And the last thing, let's talk about the integral. A lot of times when they have these integrals, they'll have something that looks like this. So they'll go 0 to x of f of t dt. Know that that just means we're doing the antiderivative of this thing. So the antiderivative of this would be 1/2 x squared. So I'm just taking the antiderivative of each one of these, plus this would be x to the third. So that would be 1/2, and then we need a 3 in the denominator to cancel, plus 1/3 x to the fourth with a 4 down there, plus x to the fifth, we still have the 1/4, need a 5 in there, plus, and then on and on and on to x to the n plus 1, okay? So then 1 over n, we have the n and then n plus 1 to cancel with this. Okay, now, could I have done this not in an expanded form? And the answer is, I do it basically the same way. So if I'm doing the expanded form, and I'm kind of running out of room here, so let me put it right here by our double derivative. And there are some exercises in the book where they have you find the intervals of convergence of these as well. And there's a connection that we'll talk about when we actually do those exercises, which you should see pretty quickly. So anyways, if we're going to integrate this 0 to x of f of t dt, realize that if I just take the antiderivative of the thing in this form, it's going to work. So let's raise that a power. Keep in mind, these are just constants, and this we still have n in the denominator. Constants don't interfere with derivative taking or integrals, times in the quantity of n plus 1. So when that comes down, I'll cancel. Do we have to worry about the index in this case? And the answer is no, it's going to stay the same. So whenever we integrate, the indexes are going to stay exactly the same. So n equals 1 is going to generate this thing. So just check it. If I plug 1 into this, notice I get 2. And if I plug 1 into this, I get 1 plus 2 times 1, so that's 2, so it does work. So once again, when we derive or integrate, we can basically leave them in the sigma form. And I'll show you an example of this. If the first term is a constant, when I take the derivative, I have to raise that index by 1. If it's not, I leave it alone. And integrate, I don't have to worry about that at all. All right, let's do one more example with these where I don't mess around with writing an expanded form. Okay, so I'm going to do the same thing here. Basically, here's our function. A will find f prime of x, B will find f double prime of x, and then C will do the antiderivative, and that typically will be in the form 0 to x of f of t dt. And I don't want to do an expanded form, so I'm just going to keep in mind what I did last time. So f prime of x, let's not worry about the bottom index yet. So let's just take the derivative. By the way, 2n factorial, it's just a constant. Don't worry about the factorial, it's just a constant, I don't know. So the 2n comes down, okay? And that drops at 2n minus 1, and then we have this over 2n factorial. Now, I can simplify this, of course, because 2n is going to be a factor of 2n factorial. So I'm going to rewrite this thing as 1 over, and now the 2n's cancel, so we're left with 2n minus 1 factorial x to the 2n minus 1. All right, now let's take a look. Was our first term a constant? So if I did my first term, and that's really all I care about. By the way, 0 factorial is just 1, so I'm not getting myself in trouble here. So this will be x to the 0, so that's just 1. So that is a constant. What that means is I have to raise this index by 1, okay? Now, if I take the derivative of this, if I take the double derivative, okay, let's do the same thing. We won't worry about the index just yet. That 2n minus 1 comes down. That drops to 2n minus 2 over 2n minus 1 factorial, okay? And let me point out that our first term here, if I plug 1 into this, I would get x to the 2 minus 1. So the x stays there. So we're not losing that term. So the n equals 1. I don't have to raise that to 2, but we can simplify it. Now there's kind of a connection here that maybe you're noticing, maybe you're not. This is going to be 1 over and then 2n minus 2. And then that's equal to x to the 2n minus 2. If you're sitting here going, you know what, isn't this and that the same thing? You're 100% correct. They are exactly the same thing, and we'll talk more about that connection later, because that power series I started with actually is a function that kind of fits together with this. And then finally, the integral, once again with the integrals, I do not have to concern myself with adjusting the bottom index. It's just a matter of just taking the antiderivative and leaving that form. So let's go ahead and take the antiderivative. So that means that we're starting with this one right here. If I raise this a power, this will go x to the 2n plus 1. So that means I need a 2n plus 1 in the denominator to cancel, and I still have the 2n factorial. So once again, some neat connections here. Maybe you're starting to see them, maybe you're not. We'll get there. So I can rewrite this in a simplified form. And we do want to simplify these because there'll be things that we need to recognize later. So this will be to the 2n plus 1. Hopefully this isn't too ugly. And then 2n plus 1 times 2n factorial will leave me with 2n plus 1 factorial. So that is how we take the derivatives and integrals of power series. So that is 8.8 power series.